NASA has spent decades trying to fly a nuclear spacecraft. Almost none ever became practical. Programs were canceled. Concepts stayed on paper. Hardware was built and then abandoned. Now, Space Reactor-1 Freedom may finally be the step toward a usable system. But this isn't really about Mars. Most people think nuclear spacecraft means one thing: getting to Mars faster. That is the story most people carry into this topic. A reactor provides enormous power. The spacecraft accelerates hard, and astronauts arrive months earlier than any chemical rocket could manage. That framing is not wrong, but speed is not the main story. It never was. That is the problem nobody talks about, and it is a problem that has never been solved. Nuclear electric propulsion works differently than most people expect. A reactor generates electricity to power ion or Hall effect thrusters. Instead of burning fuel quickly for short bursts, this approach accelerates gradually over long periods. It sacrifices brute force for endurance. The real question is not how fast a spacecraft can reach Mars. The real question is whether a nuclear system can operate continuously, reliably, and without interruption across the mission lasting months or years. The promise of nuclear electric systems has existed for decades. Programs like NERVA and Project Rover demonstrated that reactors could generate enormous energy and engines could provide real thrust. Some concepts worked in labs. Some showed results during short tests. But testing was always where the story ended. None were ever proven for sustained practical missions in space. The gap between a system that works in a test and a system that works in a mission was never closed. Reliability beyond theory was always missing. The programs proved a concept. They never proved a mission. And in space, that distinction is everything. Imagine a spacecraft operating for months with no repair crews, no replacement parts, no ground team close enough to intervene in real time. Subsystems must survive radiation exposure, thermal cycling, and zero gravity. They must continuously generate electricity for propulsion, life support, and instruments. Communications stretch across millions of kilometers with delays that make real-time decisions impossible. In that environment, working once is not enough. A system that performs in a lab and fails in deep space proves nothing. The mission is the test. Systems might perform during a short test. They might hold together for the first few weeks. But can they operate repeatedly month after month in the harsh environment that is deep space? That is the question that has never had a real answer. Not because no one tried, because no mission ever stayed out long enough under enough operational pressure to find out. Space Reactor-1 Freedom is designed to change that. The test mission will not go to Mars. It will stay on a controlled trajectory closer to Earth where NASA can evaluate system performance without the full risk of deep space operations. The goal isn't the destination, it is operational proof. But this creates a problem that most people miss. Demonstrating a nuclear system in space once proves very little. The real question is whether it keeps working when nothing can be repaired. Engineers must show the reactor operates reliably for months, that thrusters respond predictably, and that the spacecraft's energy management handles variable loads without interruption. Any failure could compromise not just this mission, but every mission planned after it. And this is where the real problem begins. Because nuclear electric propulsion is not a single technology. It is a chain of systems, and a chain is only as strong as the pressure it can sustain. Nuclear electric propulsion does not provide instant high thrust. Acceleration is gradual and continuous. Mission design must account for long-duration propulsion, not bursts of speed. Every element, navigation, power allocation, thermal regulation, operational scheduling must function correctly for months. These are not independent systems. They are interconnected layers, each dependent on the others. Space Reactor-1 Freedom must operate those layers in sequence and in parallel. The reactor provides electricity to thrusters while maintaining safe temperatures. Propulsion must accelerate the spacecraft efficiently. Sensors, control systems, and communications must operate without interruption. If one layer develops a problem, it pressures every other layer. A working engine alone is not enough if the network cannot perform consistently. This is where the system becomes fragile. Nuclear electric propulsion introduces interactions that have never been tested at this scale. Thermal management affects power output. Propulsion timing affects navigation and energy distribution. The thermal load shifts as the mission deepens. Power demand changes depending on which systems are active. These connections have never been validated under real mission conditions. Unexpected behavior in any single layer could ripple across the entire system, with no one close enough to intervene. And there is another problem NASA cannot ignore. Nuclear systems in space face regulatory, environmental, and safety constraints that do not apply to conventional spacecraft. Engineers must balance reactor performance, propulsion efficiency, and compliance with safety standards, all while operating in orbit, far from any intervention. A nuclear spacecraft does not only need to work, it needs permission to exist, and it needs to keep earning that permission across the entire duration of the mission. Then there is the industrial layer. Specialized manufacturing, radioactive material handling, and component reliability at this level are not standard capabilities. Production and testing must succeed at every step before launch. If any industrial element introduces a failure point, mission success may be compromised before the spacecraft ever leaves Earth. The question is not just whether the spacecraft works in orbit, it is whether NASA can build, certify, and operate these systems repeatedly at the scale future missions will require. Months into deep space, there are no repair crews, no backup deliveries, no replacement systems. Only hardware that either keeps working or quietly starts failing. That is the operational reality where Space Reactor-1 Freedom must survive. Not just for days, for months. That is what makes this different from every nuclear space program that came before it. If nuclear systems succeed, the implications extend far beyond a single mission. Heavy cargo could move efficiently across the solar system. Robotic missions could operate for years without resupply. Crewed missions would gain flexibility in timing and trajectory that chemical propulsion cannot provide. The spacecraft could operate where solar power becomes less practical for high-demand missions. This may eventually enable Mars missions, lunar outposts, and deep space operations that are currently not possible. But none of that becomes real without proving the system first. Because capability alone is not enough. NASA has proven nuclear systems in labs. Reactors can generate power, thrusters can fire, components can survive short tests. But none of that answers the operational question. Can these systems perform repeatedly, reliably, over months in the unpredictable environment of deep space, with no one nearby to fix what breaks? That question has waited decades for an answer. Space Reactor-1 Freedom is the first serious attempt to provide one. The outcome will influence how NASA designs deep space missions for decades. It will inform how future programs plan energy, manage propulsion, and calculate risk across missions that no one has ever attempted at this scale. It creates the bridge from theoretical designs to practical systems. Without it, Mars and deep space plans remain what they have always been: conceptual. Now, if you want to understand what space missions actually prove, not just what gets announced, subscribe to SpaceWatch. Because Space Reactor-1 Freedom does not close the nuclear story. It opens it. And once the first test is complete, the pressure shifts to everything NASA still has to prove above it. NASA is not testing a nuclear spacecraft for a single trip. It is testing whether nuclear systems can finally become dependable in deep space, across months, years, and the kinds of missions future exploration may depend on. Because if deep space missions increasingly struggle under energy, distance, and logistics pressure, nuclear systems may eventually stop being experimental and start becoming necessary. The spacecraft isn't the story. The system is the story.